the Soviet Congress was very important, especially for the 1911, the first one, because that was held in the midst of a great debate about what Planck and Einstein had done. It's interesting to notice that the report of the Congress published next year was entitled "The Theory of Radiation and Quanta." As I said last time, no mention of relativity, because relativity was already generally accepted. Here's a picture of that conference. There were only 20 people, and as I said, none of them was American or Asian. In this picture, you see Madame Curie, and that's Poincaré. Poincaré, as you know, was one of the two greatest mathematicians around the time, the other one being Hilbert. Hilbert, in some sense, was more powerful. Poincaré was more geometrical, more fluid. And at the time, there was a general perception that Hilbert was perhaps a greater mathematician because he had solved very difficult problems. And also because Poincaré's papers were oftentimes not very rigorous. But 100 years later, today, I think there are many people who say that, in fact, perhaps Poincaré is even a greater mathematician than Hilbert, because Poincaré opened several new chapters or several new fields in mathematics, namely the idea of topology and the idea of it led to chaos and all such things. In other words, Poincaré was a kind of person who struck out in new directions. Be that as it may, as we shall see later, Poincaré had a lot to do with special relativity also. And this is Rutherford. Rutherford was not yet as famous as he later became, because after this conference, he explained, he found the Rutherford atom, that the atom consists of a nucleus with electrons around it. And this is Lorentz. This one is Soviet, the one who had the money to hold that series of conferences. And there are many other important people. This is, of course, Einstein. This is Knudsen. Such people like Heisenberg and Pauli and were still teenagers. Schrodinger was not famous, so he was not invited. One central point of discussion at this Congress was about Einstein's hypothesis. Planck said at the conference that Einstein had considered light energy to be in packets. So Planck said, such hypotheses are irreconcilable with Maxwell's equations and with all the electromagnetic theories of light proposed up to now. When one considers the exhaustive experimental confirmation which Maxwell's electrodynamics was given by the most sensitive interference experiments, and when one considers the extraordinary difficulties involved with abandoning it for all electric and magnetic phenomena, one feels a certain reluctance to start destroying these foundations. So that was Planck's attitude in 1911. In other words, both Planck and Einstein emphasized the importance of h nu, but their interpretation of the meaning of h nu were different. Planck concocted the theory in his second paper and said that in exchange with the oscillators in the wall, the energy is h nu. Einstein went a step further and said, in fact, the energy in the electromagnetic field, despite his not having understood it completely, the energy is in packets of units of h nu. He, in fact, even went further than this, and the next year, in 1906, extended this idea to all oscillators, not just the electromagnetic field, and gave his theory of specific heat, which were in good agreement with experiment. So you see that there's a difference between Planck and Einstein was bolder, and that is characteristic of Einstein's physics. Now I move to the second melody, phase factor. In 1972, Dirac, who was 70 years old, had said the following: so if one asks what is the main feature of quantum mechanics, I feel inclined now to say that it is not non-commutative algebra. He said this because in the 1920s, in the late 1920s, when matrix mechanics was formulated, everybody understood that the new mechanics was based on the fact that P and Q do not commute. So for a long time it was thought that the non-commutation between physics variables was the key to quantum mechanics. But now, in 1972, Dirac said that I feel inclined now to say that it is not non-commutative algebra. It is the existence of probability amplitudes which underlie all atomic processes. Now a probability amplitude is related to experiment, but only partially. The square of its modulus is something that we can observe. That is the probability which the experimental people get. But besides that, there's a phase, a number of modulus unity, which can modify without affecting the square of the modulus. And this phase is all important because it is the source of all interference phenomena, but its physical significance is obscure. So the real genius of Heisenberg and Schrodinger, you might say, was to discover the existence of probability amplitudes containing this phase quantity, which is very well hidden in nature, and it is because it was so well hidden that people hadn't thought of quantum mechanics much earlier. This is Dirac's opinion at the time when he was 70 years old. Indeed, reflecting on the development of physics in the 20th century, we would realize that the introduction of the phase concept by quantum mechanics was an extremely important revolution. Let's recall that in classical physics there were only real numbers. Of course, I'm sure you all know that when you talk about the alternating currents, you sometimes use complex numbers to do calculations. But the meaning of that is that after you have gotten, say, the complex current, you take the real part of it, or the imaginary part of it. So the complex variable calculation was only an aid. It was not in the basic physical principles. In the basic physical quantities were all real. This was what happened in classical mechanics. But in quantum mechanics, in matrix mechanics, you have PQ minus QB equal to minus IH bar. So I enters explicitly. So in matrix mechanics, you have to have I. In Schrodinger's equation, IH psi dot equal to H psi, there is also an I. So both in wave mechanics and in matrix mechanics, I was essential. Now, of course, you can write either equation in terms of real and imaginary parts. if you write a complex equation into two equations, the real part and the imaginary part, there's no I anymore. However, if you do that, the meaning of the equation becomes not recognizable. Take either of the equation, if you write them down in real and imaginary parts, you would find that the result has no meaning. It has the structure is in the complex equation. So what I'm trying to emphasize is that I, or complex numbers, enter into physics in an essential way with quantum mechanics. Now, and what I'm going to discuss is how this happened. De Broglie was a young physicist, and he invented the idea of, in 1923, that since waves behave like particles, because electromagnetism behaves like particles, already shown by Compton effect. So he said particles must also behave like waves. And therefore, he wrote down the equation lambda is equal to h over p. The wavelength is equal to h over p. Why did he write this? Because he said that for electromagnetic photons, the wavelength is equal to h over the momentum. So he said, let's apply this also to particles. So if a particle has a momentum p, it should have a wavelength lambda. This is an extremely bold concept, and at first people didn't know how to interpret this. But Einstein recognized the deep meaning of this. So he told Schrodinger that Schrodinger should try to understand the paper of de Broglie. The de Broglie statement was experimentally in 1927 proved in two sets of experiments by Davidson and Germer and by G.P. Thomson. For this work, they received their Nobel Prize. They had beams of electrons, which can also cause interference, showing explicitly that the electron beams also behave like waves. I told you just a few minutes ago that de Broglie's work was seized upon as of profound importance, and Einstein asked Schrodinger to study it. In 1926, Schrodinger wrote 6 papers, all within the first half of the year, and these were great papers. In the first 5, he considered real solutions of the equation h psi equal to e psi. You all have studied the wave equations. H consists of 2 parts. The first part is the Laplacian, a real operator. The second part is the potential energy. For the Coulomb field, it is a real potential. So this whole equation is real. How does he interpret it? He thought of the solution, the real solution, from h psi equal to e psi, and then multiply that solution, psi, by a sinusoidal time-dependent. So what he was thinking of is a kind of stationary, of standing waves. Only in the 6th paper did he write down I h bar psi dot equal to h psi, where I explicitly occurs. This is a very interesting paper, a very interesting history of how Schrodinger went from a real equation into a complex equation. In the complex equation, I became essential in wave mechanics. The reason that I entered the matrix mechanics was that it was very natural, because it was based on the idea of Fourier transform, very much under consideration in Göttingen. In Göttingen, I had said last time that they were thinking of the coordinate x as having two indices, one for the initial state, one for the final state. And then they try to identify that with the high harmonics of the Fourier expansion of x. So the concept of Fourier expansion was very much alive in Göttingen, and therefore I was very natural. So therefore when PQ minus QP equal to minus H bar was written down, they were not surprised that there was an I, and nobody questioned why there's an I. But Schrodinger in 1926 was reluctant to accept the complex numbers. He wanted to create a wave equation for real waves in conformity with the Broglie's ideas. So he wrote down H psi equal to E psi. In one of the 6 papers, in fact, there is a footnote about the wave function psi n. He wrote down psi n. You probably recognize this actually is the harmonic oscillator solution where H is the Hermite polynomial. And this equation, of course, is an exponential with an I in it. But then he added a footnote which said I means square root of minus 1. On the right-hand side, that is the side with the exponential, the real part is to be taken as usual. As usual, it's meaning that you do this just like you do alternating current calculations. So it's very clear that Schrodinger's thinking is based, at that time, is based on the idea that you use complex numbers perhaps as an aid, but not in principle. The fundamental idea that he had was based on real concepts, on real wave functions. Thus he was thinking of standing waves. After his 3 papers were, the proofs of the 3 papers were sent to Planck, to Lorentz. On May 27th, 1926, Lorentz wrote a long letter thanking Schrodinger for sending to him the proof sheets of the first 3 articles. Then Lorentz asked Schrodinger several very perceptive questions. Lorentz was over 70 years old at the time. In fact, he died a few years after that. But he was still very, very sharp. And he asked very important questions. One of the questions was the following. Lorentz said, true equation of motion should not contain E, but contain time derivatives instead. Essentially, he is saying, for example, like in Newton's equations, the equation of motion does not contain energy. But when you integrate it, you get the constant E. So E should not be there. There should be time derivative. So Schrodinger struggled with this. We all know that the eventual equation has I and has no E. It's I H psi dot equal to H psi. There is no E, but there is I, because it's I times d dt. That replaces the E. So how Schrodinger struggled with this question, and on June 6th, that's something like 10 days later, he answered in a long letter to Lorentz. and said, what is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. Psi is surely fundamentally a real function. So he wrote down this equation. How did he arrive at this equation? He essentially take the IH psi dot equal to H psi and operate on it once more with the IH bar ddt. The left side, of course, becomes minus H bar square psi double dot. He was very happy that I was eliminated. On the right hand, he got H square psi. That he was very happy was indicated by what he wrote to Planck 5 days later. He said, by the way, during the last few days, another heavy stone has been rolled away from my heart. I had considerable anxiety over it. That means over the question that Lawrence asked him to have a time derivative. But it all resolved itself with unheard of simplicity and unheard of beauty. The unheard of simplicity and unheard of beauty was that the second derivative equation with H square, with capital H square on the right side. In this letter, dated June 11, Schrodinger also said, let the potential energy be it is possible to let the potential energy be an explicit function of the time. So when he wrote to Planck about his great success, he said that the Hamiltonian could also be dependent on time. But that is not correct. Because if you take the equation IH bar psi dot equal to H psi, if H is time dependent, if I now operate with IH bar ddt again, the left side, of course, gets to minus H bar square psi double dot. But the right-hand side now contains two terms. One contains the derivative of capital H. In his argument, he had only thought about the second term. But after his letter to Planck, he apparently looked into it more carefully and found that there is this term with an I still there. So it was only then that he realized there's no way in which you can eliminate the I. Schrodinger found the mistake in the next 10 days. And then he submitted on June 23rd the last of his 6 great papers in which this equation appears for the first time. So he finally found that it is impossible not to have I. In other words, I is essential in quantum mechanics. He called that equation, the equation that we now call the Schrodinger equation, an Eigentliche wave equation. Eigentliche sometimes is translated as real. But of course, in this context, it's very confusing to call it a real wave equation. It's perhaps should be called proper wave equation. That this evolution of Schrodinger's thinking had profound effects can be seen from the fact that at about that time, Max Born wrote 2 papers. This is a mistake. Born's 2 papers of 1926, not 25, on probability was submitted on June the 25th and July the 21st. On June 25th, these are the 2 great papers of Born which gave rise to the statement that the psi absolute value squared is equal to the probability. And those 2 papers, the first paper dated June 25th, explicitly Born said the wave equation is real, the wave function is real. Apparently, after June 25th, he got the 6th paper of Schrodinger. So a month later, on July 21st, Born wrote another paper in which the wave function becomes complex. So this shows that not only was Schrodinger changing his mind, Schrodinger's change of mind affected other people who were working in quantum mechanics. In the first, Born used the real psi. In the second, he used complex psi. The importance of phases, once it's inherent in quantum mechanics, can be seen from the fact that such ideas underlying holography, electron holography, lasers, superconductivity, superfluidity, Bose-Einstein condensation were all deeply related to the concept of phase in various aspects. So that phase is a fundamental concept in 20th century physics, is a very obvious thing. The action principle is a very well-known and ancient concept. It started with the optics, the idea of least time, which started with Fermat and with Huygens. I'm sure you all well know this idea that if you have a mirror, from A to B is the path of light. But you can think of it this way. If this is A prime is the mirror image of A, then if you try to make the light strike at C prime, then A, C prime B has a length which is equal to A prime, C prime B, because AC is equal to AC prime is equal to A prime, C prime. But A prime, C prime B is of course longer than A prime, C B. A prime, C B should be a straight line. So what that means is that the real path from A to B follows the path of least time. So this was the original idea of Fermat et al. This idea was transformed into a principle of mechanics, and is called the principle of least action. It was first proposed in 1834 by Hamilton. It is one of the great achievements in fundamental mechanics. This idea then is transformed by Feynman, who introduced the concept of I and wrote down the following. First, he defined action as an integral of the Lagrangian dt, and he considered the exponential of I times the action divided by h bar. By integrating this expression over different paths, he introduced the idea of the path integral. By integrating over different paths, you have a transition amplitude. This is Feynman's formulation of quantum mechanics. Quantum mechanics is in there because there's h bar. But this also shows in another way the essential nature of the concept of I in quantum mechanics. If you take this as a path integral, then the classical path for which S is a minimum is a stationary one, because when you take paths which are slightly different from the real path, if you take the path of least action, then the exponential is stationary in there, so they would accumulate. While if you take a path which is not the actual path, it's not the least action, then its neighborhood, the exponent varies very much, so they cancel each other in the path integral. This is a great idea. In fact, it is clear today that that is the greatest idea, the greatest contribution of Feynman to physics. In the 1950s, when I was a graduate student and later a postdoc, Feynman became very famous because of his Feynman diagrams. And indeed, at that time, Feynman's name was dazzling because you can compute transition amplitudes, scattering amplitudes with the Feynman diagrams much more easily than what people were able to do in the 1930s. But today, of course, the Feynman diagrams were still important. But what is involved in the path integral of this expression is much more profound. It's much more profound because it captures the spirit of both classical mechanics and quantum mechanics in an essential way. And also, later on, I will show that in this expression, all three fundamental melodies of 20th century physics were captured. First, there is the H-bar, so it involves quantum mechanics. Second, it's a phase factor. It's an integral over a phase factor. And third, this expression has great symmetry. If you interpret it correctly, in gauge theory, this expression you can explicitly show is very symmetrical. This is a somewhat complicated concept, which I hope I will be able to come to in one of the later lectures. And there is one more reason. The exact definition of the path integral is not yet known. The path integral is something which is not today, is not mathematically defined in any rigorous manner. But everybody who has worked with it knows that it has certain very essential features that we all can agree with without a deep mathematical foundation put underneath it. For that reason, there is a mystery around it. And because of that, it is perhaps important for the young people to pay special attention to this. You probably know the story that the delta function was invented by Dirac in the 1920s and 1930s. At that time, it was mathematically not rigorous. But later on, a French mathematician named Schwartz put a mathematical rigorous basis underneath it. That was one of the great achievements of mathematics after the Second World War. Similarly, if anybody could make a rigorous definition of path integral mathematically, that would certainly be considered a great achievement of 21st century mathematics. Now I come to a more complicated idea that gauge theory is related to the concept of phase. In 1918, Hermann Weyl was very much impressed by Einstein's general relativity. General relativity was published in 1915 and 1916. Beyond general relativity, Einstein also emphasized around that time that the electromagnetism must be geometrized. Einstein said, I have now geometrized gravity. At that time, people only knew about two interactions, not like today. We know strong interactions and weak interactions. Both of them were sort of still only something in the air. But people knew very well gravity and the electromagnetism around that time. So Einstein said, I have geometrized gravity. Electromagnetism should also be geometrized. So Weyl tried to geometrize electromagnetism. Around that time, Levi-Civita and others, that others include Weyl himself, have developed the idea of parallel transport. If in four-dimensional space you start from a point A and at that point, suppose you have a four-dimensional vector, and in Riemannian geometry, there's a natural concept called parallel displacement. If you make a parallel displacement around the four-dimensional path, then the vector, when you come back to the point A, according to Riemannian geometry, the direction may not be exactly the same. And that is one of the fundamental concepts of Riemannian geometry. What Weyl said was, on a curved surface, the parallel transported vector may not come back to its original direction. This statement is well known at that time. So Weyl asked, if so, why not also its length? Why couldn't it be that its length also changed? The crucial sentence in the 1918 paper of Weyl was, warum nicht auch seine Länge? Why not also its length? So he would propose a theory in which when you make a meter stick move around the four-dimensional path, its length would keep on changing. How does it change? He proposed a Proportionalitätsfaktor. In German, you have a tendency to make long words out of several short ones. And so he proposed that it changes by a proportionality factor. In other words, if you go from a space-time point A to a space-time point B, there is an exponential that you multiply onto the length. The exponential is written on top. And he called that a stretch factor, meaning that the length is stretched. And this was Weyl's gauge theory. And how does he identify that with electromagnetism? He said that phi mu should be proportional to a mu. So he said that if you have an electromagnetic field, then when you go along a path, the length would keep on changing by a factor dependent on the a mu along its path. This was a geometric idea of Weyl's. He wrote this paper up and submitted it for the publication of the Berlin Academy. The Academy's editors were Planck and Nernst. So Planck and Nernst naturally asked for the opinion of Einstein, because Einstein at that time was living in Berlin. And Einstein, in his characteristic physical way, wrote a review and said that the Weyl idea is ingenious, but it couldn't be correct because, Einstein said, if you consider 2 points in space-time, A and B, and if you have 2 meter sticks which are the same length at this point, and you bring 1 meter stick along this path to B, bring the other meter stick which originally was the same length along this path to B. According to Weyl, if the a mu along this field and along this field are different, then when it arrives at this point, these 2 meter sticks may not have the same length anymore. If that is the case, you cannot have standardized meter sticks. Each meter stick's length depends on its history. If that is the case, how can there be physics? So this was a devastating remark. In fact, if you think about it, it means that the Weier's idea was totally wrong. But fortunately for physics, the editors did not suppress the paper. They published the paper. They only asked Einstein to write a postscript. So if you read the paper today, there's the Weyr paper, then there's a postscript by Einstein, which raised this question. And then the editors asked Weyr to write a postscript, which is also published. If you read the postscript, you would see that what it says is that no, Einstein did not understand what I meant. But he did not clarify what precisely he meant. So therefore, the postscript really said nothing. And in subsequent years, Weyr wrote several papers. All of them were philosophical in nature, and none of them really answered Einstein's very perceptive question. Einstein's postscript said, the length of a common ruler or the speed of a common clock would depend on its history, and that is unacceptable. Entirely independent of this, in the years 1926 and 1927, a Russian physicist, Fock, and a German physicist who later went to America, London, who was Jewish, introduced an I. So Weier's exponential integral a dx become exponential integral minus I a dx. And with this introduction, Einstein's objection is removed, because what it means is that when you go from A to B, with that replacement, gauge theory becomes phase theory. If you change gauge into phase, how about Einstein's objection? From A to B, in two different paths, indeed, the resulting phase at the point B are not the same. But phase does not change the length. So as a consequence, Einstein's objection disappears. You can still standardize meter sticks. But then immediately a next question come up. Can you measure this phase difference? The answer is yes, you can. In fact, independently of this, in 1959, Aharonov and Bohm at that time was a graduate student, Aharonov at that time was a graduate student of Bohm. And they, independently of what I just told you about Weyr and Einstein, thought about in electromagnetism an experiment which is called the Aharonov-Bohm experiment. The experiment consists of the idea that if you have an electron beam which is split into two, so one goes this way, the other goes this way, and if in the empty space in between you put a long solenoid perpendicular to the screen with a magnetic field inside, but it's a well-shielded solenoid, so there's no leakage magnetic field. In that case, outside of the solenoid, there's no magnetic field. There's no electric field. So the electron in going from here to here and the electron in going from here to here suffer no electromagnetic forces. And yet they argued that there could be a phase difference. And so therefore you can have an interference pattern. If you put a screen here, you would have an interference pattern. If you have a shielded place, if you have two beams, they would interfere and you would get fringes of interference at this point B if you put a screen here. Now what Aharonov and Bohm argued was that if you now change the magnetic field from one value, say H1, to another value h2, the fringes would be different. The fringe would move depending on whether you increase the flux or not increase the flux. This was called the Aharonov-Bohm experiment. And this is, in other words, this answers the question which I just raised a few minutes ago, namely, if according to gauge theory, the two lengths, the 2 meters, the electron at this point has no change of absolute value of the wave function, but it could change phase. So you can detect the phase difference. So the Aharonov-Bohm experiment is in fact an experiment both to answer Einstein's objection to wire and also to quantitatively test it. So this was a very interesting proposal by Aharonov-Bohm, who proposed it independently of Wire and Einstein. A year afterwards, Chambers, a British experimental physicist, used a tapered magnetic needle instead of a long solenoid and claimed that he had seen the AB effect. What he did was, instead of a solenoid here, a long solenoid without leakage of magnetic field, he couldn't do that because it's very small, and he was not able at that time to manufacture such a thing. So he used a magnetic needle, a long needle, which however tapered. That means at one end it's thicker, at the other end it's thinner. As a consequence, the magnetic flux at one end is larger than the magnetic flux at the other end. So he did the experiment with a tapered solenoid. And he found that in various sections, the fringes are twisted. So he claimed that that is a indication of the Aharonov-Bohm effect. However, that was very unsatisfactory. But the leaked flux from his needle caused objection. After all, if you have a tapered magnetic needle, then the magnetic flux inside here is larger than the magnetic flux at the other end. But the magnetic flux is continuous, so it has to go somewhere. Therefore, there's leakage. In other words, in his experiment, there are magnetic fields outside of the needle. And that flux outside of the needle would affect the electron beams in a very complicated way. And there were many, many papers published discussing whether, in fact, the so-called experimental evidence of Chambers was a correct one. Finally, in the mid-1980s, Tonomura et al. Quantitatively proved the AB effect, thus introducing experimental topology into fundamental physics. This is approximately the experimental setup of Tonomura. Here's an electron beam source which is split through this into here, and it is detected here. The experiment was it uses the electron holography, and it's a highly accurate one, so that not only did they succeed in proving the Aharonov-Bohm effect, they proved it quantitatively. Now I want to go into a related different subject. Namely, Schrodinger, in fact, had proposed insertion for I in 1922. This is historically an important thing about how quantum mechanics, how wave mechanics was born. In 1922, that was 3 years before Heisenberg, Schrodinger wrote an article called On a Remarkable Property of the Quantum Orbit of One Electron. What he did was he took the Weyl stretch factor, which I had mentioned before. Weyl had this exponential. The gamma is a constant. We all know that eventually gamma should become I, should include the imaginary part, square root of -1. But in Weyl, the gamma is real. Therefore, this is a stretch factor. So in 1922 Schrodinger did was that he said, okay, let's consider this Weyl factor around the Bohr orbit. So he calculated this around the Bohr orbit. Now, the VDT is very easy to calculate because you know the potential and you know the time that it takes the electron to go around once. So he calculated this, and he found that this exponent is equal to, for a Bohr orbit, is equal to n times h around the round Bohr orbit. So the stretch factor becomes exponential nh divided by gamma. He said this is a remarkable fact. In retrospect, he was playing with some very powerful ideas, only he did not understand it. He said this is remarkable because he said the exponent is an integral multiple of a number. And he took gamma to be equal to E squared over C in his paper, and found the exponential, the stretch factor, to be this expression. He found this, he called this remarkable. But from our viewpoint, what is more remarkable is that after this main discussion, he said in some way, it's almost an accident. He said, let's take gamma equal to IH bar. And then that exponent becomes n times 2 pi divided by I. And that, of course, is where n is an integer. And that, of course, is equal to 1. If you think about this, this is the real reason why the Bohr orbit was correct. And in fact, Schrodinger had discovered this. But he did not pay any attention. Why? Presumably because he did not feel that the gamma should be complex. So even though he tried this and made this what we now regard as most important discovery, he ignored it. Then in 1925, as I told you, Einstein told Schrodinger to look at the de Broglie. And when Schrodinger looked at de Broglie, he found that in fact what he had done in 1922 is very similar to the de Broglie's idea. How do we know this? Because on November 3, 1925, Schrodinger wrote a letter to Einstein in which Schrodinger said that the Broglie interpretation of the quantum rules seems to me to be related in some ways to my note in the Zeitschrift für Physik 1922, where a remarkable property of the Weyl gauge factor, thus exponential, along each quasi-period, what he called quasi-period is a Bohr period, is shown. So in 1925, Schrodinger, upon comparing his earlier paper of 1922 with the de Broglie new idea, he realized that the two are deeply related. And so then he tried to write de Broglie's idea, which is for a beam of electrons, into a wave equation. He converts the wavelength idea into a wave equation. That was how, within 3 months, his first great paper of 1926 was born. So realizing this, we can think of this diagram. On the left side, we have wire 1918, which got changed by the insertion of I through the work of London and through work of Fogg into wire 1929, which is the gauge theory, the correct gauge theory of electromagnetism with the I. We all know that de Broglie in 1923 had an input into Schrodinger, and of course Einstein had a great input into Schrodinger. And Einstein himself at that time was influenced by Bose. So along this path, there was born the idea of Bose-Einstein condensation. But usually this one was not known. It was not known because Schrodinger, in his 6 great papers, never mentioned this 1922 paper. Why not? I had written a paper explaining or giving my explanation of why in 1926 Schrodinger, realizing the relevance of his paper of 1922, yet did not mention it in his papers. So the 1922 paper disappeared from literature for a long time until sometime in the 1970s. 2 historians of science discovered this paper and wrote a very interesting paper called "Why Was It Schrodinger Who Discovered Wave Mechanics?" And the main point of that paper, a very interesting paper, was that Schrodinger in 1926 put de Broglie's idea and his earlier paper of 1922 together and created wave mechanics. I had up to now talked about phase factor. And phase factor, of course, depends on the introduction of I. And I've also, in the last 20 minutes, emphasized how I was essential in changing Weier's gauge theory into a phase theory. Now I want to talk about a further extension of the number system, and that was called quaternions. Quaternions was an algebra invented by Hamiltonian, but by Hamilton. And he was so proud of this invention that he had the fundamental rules of quaternion algebra carved on a bridge. That was the bridge on which he conceived of the idea of the quaternions. The quaternion is something like this. Instead of x plus yi, it has not just 1 root of square root of minus 1, but 3 roots, I, j, k. So that I squared is equal to j squared is equal to k squared is equal to minus 1. And the multiplication rules of I, j, and k are given underneath. Ij is equal to minus ji is equal to k, jk is equal to minus kj is equal to I, ki is equal to minus is equal to j. With this rule, with these rules, you can prove the following: that the collection of numbers q, where x, y, z, w are all real numbers, the collection of such numbers form a associative division algebra. Associative means that if A, B, C are 3 quaternions, then A times BC is equal to AB times C. That is called associative algebra. So this algebra is associative. But the important thing is that it is a division algebra. A division algebra is one in which every quaternion other than 0, in other words, if a quaternion is such that x, y, z, w are not all 0, if at least one of them is non-zero, then it has an inverse. And so that you can then divide with it. And the division, as you can easily see, to, well, let me see what I wrote down. No. How, if you have an ordinary complex number x plus yi, if q is equal to x plus yi plus zj plus wk, then q inverse is equal to x minus iy minus yi minus zj minus wk divided by x squared plus y squared. Very much similar to the complex number. You can easily show that if you multiply these two together, you get 1. And with the proper definition of q inverse, you can now divide. So this is, once you have this, you can easily show that the whole quaternion system is a division algebra. So it is an associative division algebra. And what is remarkable is that in fact there are only 3 possible associative division algebras: real numbers, complex numbers, and quaternions. Real number is a division algebra, we all know. It's an associative division algebra. Complex numbers, we all know, is also associative division algebra. That quaternions is an associative division algebra is not difficult to show. In fact, this whole thing is deeply related to Dirac's alpha and beta matrices. Because of the beauty of the algebra of quaternions, Hamilton, once he had invented the idea of the quaternions, devoted the rest of his life to trying to write all fundamental ideas in physics in terms of quaternions. In this effort, Maxwell was very enthusiastic. So if you read Maxwell's papers, you would see that Maxwell was very enthusiastic about having vectors, but even more enthusiastic about using quaternions. If you read his treatise, which was the big tome which he wrote in his later life, the strange thing is that he did not write equations in vector form. He wrote equations in component form. The reason is because he felt that the vectors is only on the way to a complete quaternion formulation. And he had not yet formulated everything satisfactory in quaternions, so he did not put everything in vector form. So if you read his articles, they were very lengthy because they were written in component form. The one who brought vectors in an essential way into physics was Gibbs. Gibbs was not studying electromagnetism. Gibbs, as I said the last time, was a great statistical mechanician. But Gibbs was the one who emphasized that let us start using vectors. And his lectures at Yale on vectors became the textbook that spread through the beginning of the 20th century. So that by the time that I was a graduate student, Maxwell's equations, for example, were all written in vector form. But how about the quaternions? How about the original push by Hamilton and by Maxwell and by others to have quaternions into the fundamental language of the algebra of physics? The answer is still today, quaternions have not entered the physics in any essential way. And here I would introduce a sequence of arguments to say that eventually quaternion problem would enter into physics. First, quantum mechanics shows physics is built on principles based on complex numbers. This is what I have repeatedly emphasized today. The complex number system is related to a symmetry. The complex number system has the operation of complex conjugation. With complex conjugation, eventually we understand the existence of complex conjugation in the complex number system shows that there are antiparticles. In other words, there's a symmetry in nature called the particle-antiparticle symmetry. That is called charge conjugation symmetry. Charge conjugation symmetry mathematically is related to the complex conjugation operation. The complex conjugation operation is a symmetry of the complex numbers. So therefore you see that the symmetry of the complex number system has an experimental manifestation of the existence of antiparticles. So an important symmetry in physics, it is due to the number system used. It's due to the symmetry of a number system. In other words, the symmetry of nature and the symmetry of the number system were related to each other. Now the quaternions have a symmetry in its algebra, a bigger symmetry. That bigger symmetry is the rotation of the I, j, and k. It has 3 square roots of -1. If I now make a linear combination of I, j, k and call 3 linear combinations, call them I prime, j prime, k prime, then the whole algebra is symmetrical. In other words, if I have this I, j, k and I now form 3 linear combinations, a rotation of I, j, k into I prime, j prime, k prime, then you have a rotated quaternion system, and that quaternion system is also a quaternion. So the quaternion system has, instead of a reflection symmetry, a rotational symmetry of the ijk, which is a SO3 symmetry. SO3 symmetry is deeply related to SU2 symmetry. This is they are in fact the same thing, only one is a double valued representation of the other one. I cannot go into this in detail, but that the SO3, the 3-dimensional rotations, and the SU2 are deeply related is one of the fundamental facts that you have to learn when you learn about the Lie groups. The SU2 symmetries in particle physics, in fact, what people learned in the 1950s, 60s, 70s was that a fundamental symmetry of elementary particles is the SU2 symmetry. Therefore, a natural question is, are these symmetries, are these SU2 symmetries related to a theory based on quaternions? So this is a very natural question. And naturally, therefore, many people have worked on this. But so far, the result is not satisfactory. So we have to claim that today there is no fundamental theory based on quaternions which would explain the experimentally observed SU2 symmetry in elementary particles. We can also go a little bit further. Suppose the quaternions are related to the experimentally observed SU2 symmetry. Would there be further developments along that line? If you want to ask this question, you would be asking, is there a more complicated number system? Now, I already said to you that real numbers, complex numbers, and quaternions are the three associative division algebras. So if you want to generalize that, you have to go to algebras which are not associative division algebras. It turns out the next complicated number system is called the octonions. The octonions have 7 square roots of -1 instead of 3. But by the way, you might naturally ask, if a complex numbers has 1 square root of -1, if quaternions has 3 square roots of -1, why not try one system where there are 2 square root of -1? This is a very natural question. You can try that. You would find rapidly that with x plus yi plus zj, but without the k term, you cannot have multiplication rules such that the whole thing forms a associative division algebra. To make it the associative division algebra, you have to have 3. The next complex one is to have 7 square root of -1. It is the next more complicated number system. It is still a division algebra, but it's not associative anymore. In other words, x times yz is no longer equal to xy times z, but it is still a division algebra. Every number which is not 0 can still have an inverse. And it's a large algebraic symmetry due to linear transformations between the 7 square roots of -1. And that number system, that symmetry is called G2. G2 is one of the complicated Lie algebras. Lie algebra is a generalization of a discrete group. Let's say the permutation group of 3 elements, which consists of 6 permutations, is one of the simplest discrete groups. Then in the 1900s, Sophus Lie, a Norwegian mathematician, generalized the concept of groups into continuous groups. 3-dimensional rotation forms a continuous group. Then at the end of the 19th century and the beginning of the 20th century, a great French mathematician called Cartan studied all the Lie groups and found and classified all the Lie groups. There were 4 series of Lie groups. There were 5 so-called exceptional Lie groups, which had the isolated structures, and the simplest of those is called G2. So now the question is, could G2 play a role in physics? Nobody knows. There were many papers about this, but none of them is accepted because none of them had experimental evidence. In my opinion, such directions of research may perhaps be a fruitful one, because past experience told us that when you broadened from the real number system to the complex number system, you have greatly enriched physics. And furthermore, with that enrichment, there were more symmetries found. And so therefore it is natural to ask, should you go the next step into the quaternions and the next step, the octonions? But that is perhaps for future generation of physicists. Thank you. By the way, there was a Mr. Zhang who sent me an email. Which one is Mr. Zhang? Z-A? Okay, I send you 2 emails. Maybe one of these days we could have a discussion. What Mr. Zhang said was that the curve fitting of Planck does not immediately give rise to the number h. That number h, the curve fitting gives rise to exponential minus c nu over t. Nu is the experimental frequency, T is the temperature. So this is it's a complicated expression which involved this factor. And what Mr. Zhang said is that Planck factorized the C into h over k. Why? Well, it's natural because kT is a concept which is well known at that time. It is by equal partition or by k, of course, is equal to the r divided by n. So therefore, it was well known. In fact, there was an experimental value, and that is how the Planck got this number h. But once you have this number h, h nu has the dimension of an energy. So that suggests that h nu, that suggests that the concept that there's an energy unit of h nu was already latent in this formula. And perhaps that is the reason why he wrote the second paper in which he created a theory where the exchange of energy was in units of h nu. But as I've said, that theory was logically incorrect. So what is clear is that this, or what we would perhaps can guess, is that the thinking process of Planck in between those two papers was this factorization and then the recognition that h nu is a unit. And then he tried to create a theory about a wrong theory about why this number h nu. 5 years later, Einstein came along and also seized on this h nu, but pushed one step further and said that the h nu, in fact, is the energy in packets of the electromagnetic field, not of the exchange. And then next year, he even pushed that further and said that the h nu is the energy of any oscillator. But Planck did not want to accept this, and that was why in 1911 he said that statement which I showed earlier today. I would think that it would be very interesting if one of you understands German to read very carefully the two papers of Planck. After all, those are very important papers in the history of physics, and see whether Planck's thinking process is in conformity with what we just guessed. Now, what I said at the end of today's lecture about the group theory and the complicated algebra are perhaps a little bit not so easy to understand. But I believe Professor Young will give you lectures which will give you more details about Lie groups. So no questions?
Professor Yan, so when we move from real number in classical physics to the use of complex number in quantum physics in the early 20th century, the situation was that we really had something that could not be explained at that time. At that time, I mean all the atomic spectrum, black body radiation, and so on. And at the end of your lecture, you mentioned that it might be interesting to look into more complicated algebras. But before doing that, what are the things that we want to explain in exploring more complicated algebra? I mean, is there an analogous situation as in the early 20th century as it is now, that we have something unexplained and we want to explore more complicated algebra?
Yeah, a very good question. The answer is no. We do not have the experimental puzzles which were essential to the progress 100 years ago. In fact, today, physics, the environment of physics research is totally different from the environment 100 years ago. 100 years ago, there were great puzzles. I mentioned the last time that there was the question of the ether. There was the question of the atoms, of why the atoms are stable. There was the question of the specific heat. All of these were great experimental puzzles that required understanding. And the push of the first 30 years of the 20th century was directed at understanding these puzzles. Today, in terrestrial physics, in physics outside of astrophysics, things seems to be in good order. So this is a very different situation. In astrophysics, there are great problems, but these great problems require very complicated, very expensive gadgets to further explore. And each experiment takes decades rather than a few days or a few weeks. So therefore, progress is going to be very, very slow. When I asked whether quaternions or octonions could be the next foundation, fundamental foundation of physics, it was not motivated by any puzzles in experiments. It is only motivated by the fact that the symmetries are very important, and we have more symmetries than SU2. So could there be more symmetries? Could there be symmetries more complicated than SU2? And could those symmetries be related in some ways to the number system? So it is a more abstract way of trying to make progress. But having said that, I should add, namely, from what I just said, you probably would say in the next 20, 30, 40 years, probably fundamental physics could not make such a large progress as physics did make such a progress in the first 30 years of the 20th century, because of the lack of possible experimental puzzles today. I would say that's true. That is correct. So the environment in which you work are very different from the environment in which Einstein, Heisenberg, or Dirac worked 100 years ago. Is that a disadvantage? Yes, if you want to make revolutions like the Einstein revolution or the Heisenberg revolution. But on the other hand, you have an advantage. The advantage is that all those developments of atomic physics and nuclear physics have now opened the doors to many, many new sub-branches, sub-disciplines of physics and interface between physics and mathematics. So today's physics is very different, not only from 100 years ago, it's from 50 years ago. When I was a graduate student, I take, let's say, 5 or 6 courses. And after I've learned those 5 or 6 courses, well, I felt that I have a command of the whole system. The whole of physics was more or less understood by me, and I try to make progress with it. Today it's impossible. Today physics is such an enormous subject because all these fundamental developments spawn further branches. So there are many, many new areas. You cannot take 5 courses and feel that you have the whole scope of physics understood. But together with that, you have an advantage, because in each of those little new disciplines, there are problems. And if you can make progress, you can make progress in many more things. In other words, there are fewer big problems. There are many more small problems. So you have a disadvantage, but you must realize you have also a great advantage. And what you need to do is look into many of these small problems. And here this is related to another topic, which is oftentimes asked to me by graduate students. The question is, should I work on big problems or should I work on small problems? Well, when I was a graduate student in Chicago, Enrico Fermi, a great physicist and a teacher at Chicago, had been asked by us graduate students the same question. He said his philosophy is one should most of the time work on small problems, and one should work on big problems only occasionally, and also one should not be obsessed with big problems, because if you exclusively work on big problems and become obsessed with it, you might become psychologically imbalanced. And indeed, such a psychologically imbalanced physicists are quite easy to find. There are many such. So it is not healthy. It is better to start with small problems.
I want to ask, you said that Einstein wants to use the approach of geometry to explain the electromagnetism.
Pardon?
You said that Einstein wants to use the geometry approach to explain the electromagnetism.
Yes.
And is it the geometry approach is the right approach to explain more physics besides gravity and electromagnetism, or is it we can treat that the geometry is a kind of algebra such that we can use other algebraic system to including more physics other than gravity or electromagnetism?
Einstein did repeatedly say that he wanted to geometrize electromagnetism. Later on, he changed it slightly and said he wanted to unify all interactions. Of course, I guess if you unify gravity with electromagnetism, since gravity is geometrical, that means electromagnetism is also somewhat geometrical. Now, what is our understanding today? With the gauge theory understanding of electromagnetism, after the 1929 paper, after Tonomura, we know that the gauge theory of electromagnetism is correct. And as I shall tell you later, that gauge theory became generalized, and now we find that not only electromagnetism is a gauge theory, but the strong and the weak interactions are also gauge theories. So today, of the four theories, three of them, strong, weak, and electromagnetism, are all gauge theories. Is gauge theory a geometrical system? It's difficult to answer that question, but today gauge theory is formulated mathematically as a fiber bundle theory. Now, fiber bundle is somewhere between geometry and analysis and algebra. Today's mathematics has the characteristic that all the fundamental ideas are related to each other. Geometry, algebra, analysis, topology, all of them are in the same direction, and fiber bundle is an essential idea. So you might say that today, yes, we have geometrized electromagnetism, we have geometrized strong and weak interactions, but today the fundamental problem is that somehow these cannot be married with gravity. Gravity, the classical theory of gravity is geometrical, that's very obvious. But that to make gravity together with quantum mechanics, that is the great difficulty. And that difficulty has occupied physicists for the last, at least the last 30 years. And it is many of the brightest young people are working in that. In particular, you must have heard of the idea of the string theory. But so far, the string theory has not yet produced any success, although it produced a lot of mathematics and a lot of intellectual challenges. So this is another aspect of the development of the style of development of physics, which makes it very different from the style of physics development 100 years ago. You know, so we have great success, and we have some great unsolved problems, and these great unsolved problems has been struggled with for 30 years, but today I would say the net result is that that struggle has not been successful.
So we want to find an algebraic system can describe all the things at the same time.
Yes. What I said in the last hour or so was in one direction. I was raising the question of whether enlarging algebraic system would work. There has been some work in that direction, but also without success. That is, however, not the main push. The main push in the last 30 years of the remaining major problems in fundamental physics was the idea of string theory. But that so far is attracted many people, but has not produced any successes. And in fact, recently there are several books criticizing the whole effort of string theory. That is now a very hot topic on the web and in the physics literature.
Is string theory is also a type of gauge theory? Is string theory a type of gauge theory?
No. String theory, in a few words, is something like this. Since people have tried to crash through the last major difficulty in unification, the idea of unification is a very powerful idea and has been greatly successful. So strong, weak electromagnetic theory have been unified under one banner, that is the gauge theory. So that's very successful. But gravity resists being incorporated into the whole system. That gravity is very much related to gauge theory is obvious. But how, and in particular how to do it in quantum mechanical way, is the great problem. So faced with that problem, some people try to strike out in a new direction. And that direction is not along the gauge theory direction. They say that in fact the field concept itself need to be changed. So field concept says that there are fields at every space-time point. And they say that maybe you should, instead of thinking of it in terms of a point, but in terms of a string. So that's why it's called a string theory. What string theory is doing is that it tries to have mathematical structures in high dimensions, which, when reduced to 4 dimensions, create structures which would both create gauge theory structures and gravitational structures. This is the rough direction in which they are working. But so far, there is no concrete string theory proposal which can be compared with experiments. And that's where the criticism now is leveled against them. People say that you have all these frameworks, but you don't have a concrete theory. So string theory, according to these criticisms, is not a theory. And there is some element of truth in that. I think for a graduate student, it is useful to know a little bit about these general directions. But the important thing is to concentrate on the concrete, already understood things. For example, about the fundamental structure of gauge theory, I think it's something that a theory graduate student must understand. And for an experimental graduate student, I think the important thing is to go into a field where there's new development. For example, Bose-Einstein condensation. That's a thriving field. It's one of the most exciting fields in the last 10 years. And it promises additional new developments all the time. That is the kind of direction in which an experimental graduate student might find a niche in which he or she can make great progress.
Why it is only the magnetic field enters the AB effect? What about the electric field?
You are asking whether any gauge theory would have what is similar to AB effect. Is that your question?
No. In AB effect, the field is the magnetic field.
Yes.
If we replace the magnetic field
yes.
with the electric field.
Yes, there is. In fact, in the original paper of Aharonov Bohm, there were both proposals. The electric one is very difficult to do. So far, it has not been satisfactorily done. It's very interesting that when Aharonov and Bohm proposed the 1959 paper, they didn't know about Einstein's objection to Weyr. In fact, these were completely different fields, and many people did not believe Aharonov Bohm. The reason is because in the early 20th century, up to about 1960, people were drilled with the idea that the electromagnetism means electric and magnetic field. The potential, A mu. If you have a flux here, then outside of the flux there's E is equal to 0, H is equal to 0, but A is not equal to 0. Because if you go around it once, you would realize that A cannot be 0. So, but everybody was taught, when I was a graduate student, I was taught that electromagnetism means E and H. It does not mean A. Why it does not mean A? Because A is flexible, and E and H are very concrete. They are directly experimentally measurable. A is not directly measurable. So we were taught that the E and H determines the electromagnetism. What Aharonov and Bohm showed is that that is not true. Even though you have no E, no H, since you have an A, you have detectable effects. So that was the main message. I remember that in the early 1940s, there were great debates in every physics department about whether Aharonov and Bohm were saying something correct or wrong. But of course, even before Tonomura's experiment was done in 1980s, gradually people began to realize A is in fact more essential than E and H. Only you have to understand A in a more flexible way. It is in fact the flexibility of A that creates electromagnetism. So it's so we now have more sophisticated understanding of electromagnetism, and when you generalize that, you can ask the same questions about non-abelian gauge theory. It is also a gauge theory. It also has what's similar to E and H. It also has what's similar to A. But all of this got more complicated. Well, in the next two lectures that I will give, I will go to the third subject, symmetry, which is a more complicated but more all-embracing subject in contemporary physics.